Hello, hello, hello. In this worked example, we're going to be exploring an important application of the work kinetic energy theorem, wind turbines, the process of taking energy that's in the form of kinetic energy of moving air, of wind, and ultimately transforming it into electrical energy to power the electrical grid. And it's a great example of using the physics that we're learning in Physics 107 to see some really practical and important applications. The wind, after all, is free and it doesn't emit any carbon dioxide or other greenhouse gases. So it's an important and ever-growing part of the story of how, through some cleverness, humans can begin to address the catastrophic effects of climate change. So let's dig in. So let's start by taking a closer look at this sort of cartoon version of what goes on in the wind turbine. Let's imagine that the rotor, these blades on the wind turbine, have a diameter, uppercase D, and therefore there's an area associated with this diameter. This is the area A of the wind that's being intercepted by the rotor on the wind turbine. And of course, A and D are simply related. A is just pi times D over 2 squared. And let's assume that the wind is blowing from left to right at a constant velocity v, so a speed given by the magnitude of that velocity v. And let's calculate how much kinetic energy there is in a cylindrical volume of cross-sectional area A and a length that we'll call L. So the kinetic energy contained in the wind in that volume is just, of course, 1/2 times the mass of the air, of the moving air, which we'll call m, times its speed squared. And we can write the amount of mass in that cylindrical volume as just the density of air, rho, times the volume of our cylindrical volume, which we'll call uppercase V, uh, and then we have a v, lowercase v squared here. And the volume of a cylinder is just the area times the length, so we can rewrite the kinetic energy contained in the moving air as 1/2 rho, the density of air, times this area A times this length L times V squared. And then let's ask how much kinetic energy is contained in the air that passes by the turbine during some fixed amount of time, delta t. So during a time interval, delta t, the length of air that passes by, this quantity lowercase l, is just equal to v, the speed of the wind, times delta t. So during a time interval delta t, the kinetic energy that passes the blades of the turbine is what? It's 1/2 rho times A. And for L, I'm going to plug in this V times delta T. And then we have a V squared here. I'm just plugging in to this formula here and substituting this quantity L here. Okay, so I can write the amount of energy, that kinetic energy that passes the wind turbine during a time delta T is just 1/2 rho times A, and there's a V times a V squared, so that gives a V cubed times delta T. And I'm ultimately interested in calculating the amount of power that can be generated by So power, that's the rate at which energy is being consumed, and power, that is just an energy divided by a time. So the power in this case that can be delivered is I just have to divide the amount of energy that passes by delta T. And when I do that, clearly the delta T's are going to cancel. So what do we get? We have this 1/2 rho A V cubed times delta T divided by the time interval delta T. These delta T's cancel, and I have this final result that the power contained in the passing wind is 1/2 rho A V cubed. And that's an important result. There are sort of two things to really focus on here. One is that the power is proportional to the area of the turbine. So it's going to push us to build turbines that have very big areas and hence very big diameters, because the amount of power that you can get out from a single turbine is just proportional to the diameter squared to the area. And also, and this is really important, the power is proportional to the wind speed to the third power, the wind speed cubed. And that means you really get paid a substantial bonus by operating windmills when there's high wind speed. It's greater than you might think. You know, doubling the wind speed, for example, increases the power by a factor of 2 cubed or 8. So that's an enormous benefit to operating wind turbines in regions where the wind is high. Now, it's worth pointing out before we go any further that not all of this power is available to be transformed into electrical energy, because the wind can't just simply stop when when it passes the wind turbine. You can't remove all of the kinetic energy, because if you did, the wind would just pile up. So what happens in practice is the wind doesn't stop, it slows down, and it also sort of expands its area, so you can end up getting a steady flow of wind by the turbine, and you're just extracting some fraction of the total kinetic energy that's contained in the incident wind. But it ends up being a surprisingly high fraction. It turns out that you can get about 60% of the kinetic energy extracted by a modern wind turbine design. And 60% of this quantity is still a pretty big number. So let's see how to analyze the situation a little bit more carefully and do it for a particular set of numerical parameters. So the first thing I want to talk about is I want to connect our discussion to the work kinetic energy theorem that we've been discussing. And the work kinetic energy theorem states that if you've got some system, you can calculate and really, strictly speaking, that system should be a single particle. If you have a system which is a single particle, you can calculate the change in the kinetic energy of the particle by looking at the work that's done on the particle by the external surroundings. Now, how does that relate to the present case? The wind is not, this moving air is not a single particle. But for the purposes of this problem, we really, if we assume, and it's not a bad assumption, that all of the air molecules are moving in the same direction at the same velocity, then you really can, for all intents and purposes, treat the moving air as if it were a single particle. So we will be able to apply the work kinetic energy theorem. And so the system in this case, let's be very explicit about it. We're going to draw a dotted line around this section of the moving air, and we're going to apply the work kinetic energy theorem. The delta K, as this system of air moves past the turbine, delta K is going to be a negative quantity. So that means that the wind turbine, the surroundings, the blade of the turbine, is going to end up doing negative work on the air. And basically, from Newton's third law, that means that the air is doing positive work on the turbine. So that's the idea, is that we can do work, the moving air can do work on the turbine, and that work can be converted into electrical energy by the turbine. Okay, so here's an example sort of featuring the current state of the art, which is really quite amazing. So General Electric, which used to make electrical turbines powered by steam, has now gotten into the business of making electrical turbines powered by wind. And the scale of these things is just enormous. They're designed to be located offshore, near the coast, but offshore where the winds are steady, and we can build very tall structures. The diameter of the rotor here, the diameter of just the blades in this design is 220 meters. And just to give you a scale, the whole thing, by the time you get it on top of the tower, is about 260 meters high. And that's pretty comparable to the Eiffel Tower, if you're familiar with that structure, or if you've walked around New York and seen the Chrysler Building, which when it was built was the tallest building in the world. These turbines are almost as tall as those impressive structures. Just the central portion here, to give you a sense of scale, just where the blades attach to the post here, that's this part here, and there's some people standing beneath it. So these things are just enormous. And let's see why, and look at the scale of the rotors here. This is actually a competitor. These rotors are, the blades here are made by Siemens here. That's a competitor to General Electric, and it gives you some sense of the scale of the individual blades. Just transporting these things is really hard. Anyway, let's do a calculation. How much electrical power do you suppose can be generated by one of these monstrosities, assuming a not particularly high wind speed of 10 meters a second? That's about 25 miles per hour. So we're going to use the expression, the upper limit on the power that you can get, we wrote down previously, is 1/2 rho, which is the mass per unit volume of air, times the cross-sectional area of the rotor, that's A, times V cubed, where V is the wind speed. And I'm just going to do a rough calculation here. The density of air, very roughly, is about 1 kilogram per cubic meter. And the area, cross-sectional area of the rotor is pi times the diameter, which we'll call, let's make it even, 200 meters divided by 2 squared. So that's pi 200 divided by 2 is 100. So let's just call this roughly pi is about 3, and 100 squared is about 10 to the 4th meters squared. So the electrical power, the upper limit on it anyway, is going to be 1/2 times 1 kilogram per meter cubed times 3 times 10 to the 4th meters squared times 10 meters per second cubed. And that's equal to 1.5 times 10 to the 7th, and the units, if we're being careful, work out to be kilograms meters squared per second cubed, and that is 15 million watts. That's 15 megawatts. Now, as we said, you can't get all of that energy out, but you can get about half of it out. So the actual answer, what General Electric will say, is that the actual power that these turbines can generate is on the order of 5 to 10 megawatts. And you get up to 10 megawatts if the wind blows a little faster than 10 meters a second. Now, just to put that number in perspective, a typical home might use at 10 kilowatts of electrical power on average. So that means that this single turbine can power something like 5 to 10,000 homes can be powered by a single one of these things. So that's basically the town of Wellesley could have just one turbine supplying all of our electrical needs. So that's really quite fantastic, and people are very interested in wind energy. Now, of course, there are some problems. The wind, while it's free, it doesn't blow all the time, and when it does blow, it doesn't always match when people want to use the energy. So that's a problem. And these things are big, and nobody wants them in their backyard. And even putting them offshore is a problem. A lot of people don't like these things offshore. They kill a lot of birds, and they make noise, and they ruin the view. There's a big wind farm that's being constructed off the coast of Cape Cod, and a lot of the people with beach homes there are very upset about that. But when you think about the big picture about climate change and the threats that the planet is facing, wind energy is really an attractive option, I think. So that's it for this worked example. Hope to see you again soon. Bye bye.